Okay, hello everyone. In a new video. In this one we are going to solve an exercise related to mechanics and the chapters of mechanical actions and equilibrium of a body. This exercise was a previous one in the brevet exams in 2019 second session, exercise number 4. The title of this exercise is magnetic force. An iron ball B of mass m and of center of gravity g is suspended to the free extremity of a spring balance which indicates 3 newtons as shown in the document 4. Then they mentioned document 4. Now we are allowed to use it. Notice that till this moment they didn't mention anything about document 5, then we are not allowed to use it. So in number 1, they are telling me that B is at equilibrium under the action of two forces. 1.1. Give the name of each force. So because the ball B has a mass m, then it will be directly subjected to the weight. So one of these forces is the weight W. And here, because we have spring balance, or in other words, here we have the string. And whenever we have a string, we know that the tension force exists. So we have the tension T, which is along the string, or due to the string. Now in 1.2, they are telling me indicate for each force, whether it's a contact force or force acting from a distance. Let's start by the weight W. We know that the only three forces that are classified as an action at a distance, they are given by the weight, the magnetic and the electric force. Therefore, the weight W is classified as an action at a distance. And all other forces are classified as contact forces, in particular the tension T. Then the tension T is classified as a contact force. Now in 1.3 they are telling me write the vector relation between these two forces, knowing that the ball B is at equilibrium. So the vector relation here is given by the condition of equilibrium. Then let's say at equilibrium. Then how do you apply this condition? Always on the left we write the sum of forces acting on the ball B, and they are given by the weight W vector plus the tension T vector. And on the other side of this equation, we write the zero vector corresponding for the condition of equilibrium. Now moving the tension T to the right hand side of the equation will give us W vector is equal to the minus T vector. Now the first equation tells us that both forces W and T act on the ball B in order for it to be at equilibrium, which means the zero vector, whereas the other equation tells us that both forces have the same line of action, opposite direction, and same magnitude. Now in 1.4, determine the mass m of B take G is equal to 10 Newton per kilogram. Then in order for us to calculate the mass m, we need to know the weight W of the ball, and the G is given by 10 Newton per kilogram. Now from the indication of the spring balance indicates 3. So the magnitude of the weight W is given by 3. Since the scale is in newtons, so the value of W will be in newtons. Now knowing that W is equal to 3 newtons, so weight is equal to M multiplied by G, constructing the triangle of this formula. Here, because we have multiplied, then W will be at the top, M and G at the bottom. Knowing that we are interested in calculating the value of M, so putting our hand over M will be given by W divided by G. The value of W is given by 3, and the value of G in the SI is given by 10. Now plugging this fraction on the calculator, it will give us 0.3. Since both W and G are in the SI, so the value of M will be in the SI, which is kilograms. Then the mass of this ball is given by 0.3 kilograms. Now in number 2, they are telling me a bar magnet is placed below B as shown in document 5. They mentioned document 5, then now we are allowed to use it. The indication of the spring balance increases due to the magnetic force F exerted by the magnet on B. So previously in document 4, the indication of the spring balance is given by 3 newtons. When we place the magnet under the ball B, the spring balance, the indication of the spring balance changes from 3 to 4 newtons. In other words, the indication of the spring balance increases due to the magnetic force F exerted by the magnet on B. Now in 2.1, indicate the line of action and the direction of F. In order to determine the line of action and the direction of F, let's represent the force F on document 5. So we know that the force F, which is the magnetic force exerted by the magnet on the ball B, and knowing that the magnetic force is classified as an action at a distance, so the point of application of F will be the center of gravity G, and it will be directed toward the center of the magnet. Like this. Knowing that this point represents the center of the magnet. Then, in this case, we can deduce that the line of action is vertical. And the direction is downward. Now in 2.2, the magnitude F of F is 1 in newtons. Represent F at a G using the scale 1 centimeter corresponding to 0.5 in newtons. Now by represent means we need to draw the vector F using the following scale. So knowing that each 1 centimeter corresponds to 0.5 in newtons, and the magnitude of the force F is given by 1 in newtons. Now, in order for us to be able to represent the vector F, we need to determine the length of this vector because the ruler is graduated by centimeters and not by newtons. So now, if we crisscross, then 1 in newtons multiplied by 1 centimeters divided by 0.5 in newtons, it will give us 2 centimeters. Then the length of the vector F is given by 2 centimeters. Knowing that here they are telling us represent F at G, so G represents the point of application of the vector F. Then F acts at the point G vertically downward. So this is the vector F. The length of this vector is given by 2 centimeters, which is worth of 1 in newtons. And by this we have finished solving this exercise. Hope it was beneficial for you guys out there watching it, and see you soon in another one.